Welcome back to AI.Code.Cast. You know we love to break down those classic coding challenges, and today we're going to be looking at the two-sum problem.
Ooh, fun.
Yeah, so just imagine, you're going through this like jumbled pile of numbers, and you need to find the two that add up to a specific target.
I like that imagery.
Yeah.
And what's really cool is how this problem pops up in so many different places.
Yeah.
Think of like optimizing database queries or even in like financial analysis.
Yeah,
Finding those efficient solutions can make a big impact no matter what you're working on.
absolutely. And speaking of efficient solutions, you brought like a ton of research on different approaches. So why don't we break down this two-sum problem together? You've got this list of numbers, right? And then there's this specific target sum in mind. The mission, if you choose to accept it, is to find the two numbers within that list that add up perfectly to your target.
Now, there are a couple of rules to make things a little more interesting. You can only use each number once, and there's always exactly one solution just waiting to be discovered.
Ooh, okay. A numerical treasure hunt. Love it.
Yeah.
So let's start with that most straightforward approach, the one that everyone probably thinks of first, brute force.
Yeah.
It's kind of like trying every single key on a giant keychain until you find the one that unlocks the door.
Yeah.
You just keep going through each number in the list and compare it to every other number to see if they add up to your target.
Yeah, and that is very intuitive. But
Yeah.
can you imagine if your keychain had thousands of keys? Brute force can get pretty slow as that list grows.
For sure.
The time it takes to solve it grows exponentially with the number of items in the list. So for massive data sets, brute force might not be the best.
Okay, yeah, that makes sense. So let's say, just for example, we had a list like this, 2, 7, 11, 15, and our target was 9. How would brute force tackle that?
Well, I'd start with comparing that first number, the 2, with every other number in the list. So 2 plus 7, 2 plus 11, 2 plus 15,
Okay.
and boom, 2 plus 7 equals 9.
Right away.
Right away. So we're done. We've got our pair.
So the solution would be the positions of those numbers in the list, right? So like in this case, it'd be 0, 1, because the 2 is at index 0 and the 7 is at index 1.
Exactly, you got it. You've cracked the code. But now think about a list with hundreds or thousands of numbers.
Oh, yeah.
Brute force would be doing tons of these comparisons.
Right.
It would be really slow.
Okay, so brute force, easy to understand, but maybe not the best when it comes to speed.
Yeah.
So what are some other ways to approach this problem? Something a little bit more, I don't know, elegant.
Ooh, I like that. So let me ask you this. Imagine you're looking for a specific book in a massive library.
Okay.
Would you go shelf by shelf checking every single book? Or would you use the library's catalog to find its exact location?
Oh, I would definitely use the catalog. Who has time to wander around a library for hours?
Exactly. And in the coding world, that's kind of what a hash table is. It's like a super organized catalog for your numbers, making those lookups super fast.
Ooh, okay. I'm intrigued. How does this hash table magic help us find our two numbers?
Well, let's stick with that same list, 2, 7, 11, 15. And remember, our target is 9. Instead of comparing every number to every other number, we can use a hash table to quickly check if the complement of a number exists.
Okay, complement meaning...
The number that when added to the current number would equal the target sum.
okay.
So if we're looking at the number 2, its complement would be 7 because 2 plus 7 equals 9.
Gotcha.
And a hash table basically lets us store each number from that list along with its position so we can super quickly check for these complements.
So it's like we're trading a little bit of space to store the hash table,
Right.
but we're gaining a lot of speed because we don't have to check every single combination.
Exactly.
You got it. Okay. I like where this is going.
Good. Now, there are a couple of popular ways to use these hash tables for the two-sum problem. There's the two-pass approach and the one-pass approach.
Two pass, one pass. Ooh. Okay. Let's dive into those. All right, so we've got these two-path and one-pass hash table methods. What's the difference?
Let's start with that two-pass method.
All right.
Okay. Imagine you've got this giant stack of papers, each with a number written on it.
Okay, lots of papers. Got it.
The two-pass method is like going through that stack twice, but with a very specific purpose each time.
Okay, I can see that giant stack.
Yeah.
What's the goal of that first pass through the papers?
The first time through, you're basically creating a table of contents. You go through each paper, noting down the number and its position in the stack. This table of contents is our hash table. So if our list is 2, 7, 11, 15, Our hash table would say, okay, 2 is at position 0, 7 is at position 1, and so on.
So we're making like a quick reference guide.
Exactly. And then what about that second pass? What are we doing then?
Yeah, what are we doing in that second pass through the papers?
Now we've got our trusty table of contents, right? So we go through the stack again. But this time, for each number, we calculate its complement, the number needed to reach that target sum.
Okay.
Let's say our target is 9, and we pick up the paper with the number 2 on it.
Okay.
The complement would be 7.
Right, because 2 plus 7 equals 9.
Exactly. So what do we do with that complement?
Yeah, what do we do?
We use our table of contents. We flip through it and see if a 7 exists.
Oh, and if it does?
We've found our winning pair. And because we have that hash table, we can see exactly where both numbers are in our original list.
So instead of comparing every number to every other number, like with brute force,
Yeah.
we're using this hash table to quickly look up the complement.
Exactly, you got it. And that's what makes the two-pass hash table method so much faster than brute force, especially when you're dealing with those really big lists of numbers.
Okay, 2-pass hash table.
Got it.
But you mentioned this 1-pass approach as well. Is that even faster?
You could say that. It's like if we were streamlining that library search even further, imagine building the catalog while you're looking for that specific book.
Whoa, multitasking at its finest.
Yeah.
So how does this 1-pass magic work?
Well, in the one-pass approach, we're doing everything at the same time. As we go through the list, we're both building our hash table and checking for those complements. So for each number, we calculate its complement and see if it's already in our hash table.
And if it is?
Jackpot. We've found our pair, and we can instantly return the index of both numbers because we cleverly stored it all in our hash table.
Ooh, I like it.
Yeah.
And what if that complement isn't in the hash table?
Then we simply add the current number and its index to the hash table and move on to the next number in our list. It's like adding books to the catalog as we find them.
So instead of 2 separate passes, like the 2-pass method, we're doing everything all at once.
Precisely. It's elegant and efficient, which is why a lot of people consider the one-pass hash table method to be the best solution for the two-sum problem.
It's amazing how using the right data structure like a hash table can totally change how we solve a problem. It's like having a secret weapon.
It really is. Now let's switch gears a bit. What if we knew our list of numbers was already sorted?
Sorted, you mean like in numerical order? How would that change our approach?
If our list is sorted, we can use a technique called the sorted array two-pointer approach. Imagine you've got 2 fingers, one pointing at the beginning of the list and the other pointing at the end.
Okay, got my 2 fingers ready. What do I do with them?
You add up the numbers that your fingers are pointing to and see if they equal the target.
And if they do...
You found your pair. Easy peasy.
But what if they don't add up to the target?
That's where the strategic finger movements come in. If the sum is less than our target, you move your left finger one position to the right, trying to make that sum bigger. And if the sum is greater than the target, we move the right finger one position to the left to make the sum smaller.
So we're like narrowing down the possibilities with each move. Like a game of hot and cold, but with numbers.
Exactly. We're taking advantage of that sorted list to avoid extra work. No need to compare every single number.
This sorted array approach sounds really efficient. So what's the catch?
Well, the two-pointer part is super fast, but we do have to account for the time it takes to sort the list in the first place if it wasn't already sorted.
So there's a little bit of overhead involved in getting everything in order.
Exactly. But if our data is already sorted naturally, like maybe it's time series data, then this approach can be a real time saver.
It's so cool how the type of data we have can influence which algorithm we choose. So we've got these different approaches for solving. Two-sum brute force, hash tables, 2-pointers. When would we use each one?
Well, if you're just starting out or working with a really small data set, brute force can be a good way to get your feet wet. It's easy to understand, and for a small number of elements, it doesn't really matter which approach you use in terms of speed.
So brute force is like our trusty screwdriver, perfect for those small, quick tasks.
Exactly. But when you're working with a lot of data, things change. Efficiency becomes super important, and that's when hash tables really shine. They give you a big speed boost, especially as the size of your data grows.
So for those bigger projects, a hash table is like our power drill, fast and efficient.
Precisely. And like we said, if your data is already sorted, the two-pointer approach can be super efficient too. It's like having a specialized tool for a very specific job.
It sounds like we really need to understand both our data and the problem we're trying to solve to pick the best approach.
Absolutely. There's no one right answer. It all depends on the context.
This has been an awesome deep dive into the two-sum problem. We've looked at the problem itself, different solutions, and even talked about some potential pitfalls.
Hmm.
But before we wrap up completely, I wanted to throw out one final thought-provoking question for our listeners.
Ooh, I like it. Hit me.
We've been talking about finding two numbers that add up to a target,
Right.
the classic two-sum problem.
Right.
But what if we wanted to find three numbers that sum to a target? Or even nay numbers?
Ooh, that's a good one. That takes us into the world of more generalized algorithms. It opens up a whole new level of problem solving.
Exactly. It's something for our listeners to think about and research. It might even inspire us for a future deep dive.
Absolutely. Until then, everyone keep those algorithmic minds sharp.
And we'll see you next time on AI.Code.Cast. So we've covered a lot of ground here, talking about all these different ways to solve the two-sum problem. We've got brute force, hash tables, even that two-pointer method on a sorted list. But before we wrap things up, I wanted to touch on something you mentioned earlier about picking the best approach for the task at hand.
Yeah, that's super important. It's like having all these different tools in your toolbox. You wouldn't use a hammer to tighten a screw, right?
Right. So how do we know which tool to grab when we're faced with a two-sum problem?
Well, if you're just getting started, or if you're dealing with a really small set of numbers, brute force can be a good way to get a handle on the problem. It's easy to understand, and for a small number of elements, it doesn't really make a difference which approach you use in terms of speed.
So brute force is kind of like that trusty screwdriver. It's perfect for simple, quick jobs.
Exactly. But when you start working with larger data sets, that's when efficiency becomes really crucial. That's where hash tables come in. They can give you a massive speed boost, especially as the amount of data grows.
So for those big projects, a hash table is like our power drill. Gets the job done fast.
Precisely. And remember, if your data is already sorted or if sorting it is just part of your normal process, then the two-pointer approach can be incredibly efficient too.
Yeah, it's like a specialized tool for a very specific job. It seems like knowing your data and the problem you're trying to solve is key to picking the best approach.
Absolutely. There's no one-size-fits-all solution. The best choice depends on the specific context of the problem you're trying to solve.
This has been such a fantastic deep dive into the two-sum problem. We've explored the problem itself, looked at all these different solutions, and even discussed some common pitfalls. But before we sign off, any last words of wisdom for our listeners out there?
Just remember that coding is all about exploring and discovering new things. Don't be afraid to try out different approaches, test your code thoroughly, and never stop learning. There's always something new and exciting waiting to be uncovered in the world of algorithms.
And on that note, from all of us here at AI.Code.Cast,